All right,
This
everybody.
meeting
So,
is being recorded.
all right, everybody. So it's a pleasure to have this week's science call presented by Aaron Tohuvavohu. Did I get it right, or did I get the syllables backwards?
That was just fine.
Okay, great. All right, and Aaron's going to talk about prompt localization of gravitational wave events and other multi-messenger things. And as we go on in the discussion, if people want to talk about prompt localization, neutrinos, and some things that Aaron may spend less time on, I think that would be great too. So whenever you're ready, Aaron.
Yeah, great. Let me share my screen again. Can you confirm that you can still see this?
Yeah, looks great.
Great. Thanks, everyone. I'm really excited today because, well, I love STROBE-X and I know everyone does too. And I'm going to talk today, I think, about an opportunity that exists for STROBE-X to enable localization of a gravitational wave detected binary neutron star merger that gives us immediate access to the post-merger environment. And I'm going to talk about that in the context of, well, why we want to do that, and in the context of Swift-BAT and the coded aperture instrument in BAT as an analog to what we might want to do for the wide field monitor on STROBE-X. Okay, so jumping right in, there are compact binary mergers. They exist in the universe. The outcomes of the merger is highly dependent on the masses of the binary components. In particular, for binary neutron stars, the post-merger remnant, whether it's a hypermassive neutron star that's supported by a differential rotation from collapse, whether it's a stable neutron star that lives long, whether it collapsed directly to a black hole, whether a disk forms or not, depends crucially on the masses and the mass ratio. And the outcomes can be very different. If you're interested in the post-merger remnant, which I am, and I think a lot of other people are, whether a neutron star survives for 100 milliseconds or longer, or doesn't form at all and you have prompt collapse to a black hole, has strong effects on the post-merger environment and the electromagnetic emission that comes out. The binary neutron star mergers, of course, are very rich phenomenological settings. There's emission that comes out on from gamma rays to radio, and on timescales from seconds to years post-merger. What you're looking at on the left is some sort of cartoon diagram that on the bottom panel shows a cartoon of the sort of physical emission processes that are taking place as a function of the time around the merger time, and on the top panel something about the radiative emission processes, whether they're in gravitational waves or electromagnetism. In particular, if you find a gravitational wave electromagnetic counterpart, you can do the standard siren technique, whereby you directly measure the Hubble constant. If you have the gravitational wave, the luminosity distance that you infer from the gravitational waves, and you find the electromagnetic counterpart and measure its redshift or the redshift of its host galaxy. But we don't want to just find these things, right? To do that, all you have to do is find the electromagnetic counterpart. But we don't want to just find them. We want to find them quickly. And the reason we want to find them quickly is, as you see on the left, there's a ton of very interesting physics and very interesting phenomena to study at the earliest times post-merger. Seconds to minutes to the first few hours of the post-merger environment are very rich. The system is evolving very rapidly, and we want to see and peer right into that. For context, and I'll talk about this in a second even further, 170817, the one electromagnetic counterpart to a binary neutron star merger we've seen so far, was found at T0 plus 12 hours, just with a single photometric data point, and sensitive multi-wavelength characterization didn't begin until much later. So we missed out on all of the early time awesomeness. Just so everyone's on the same page, this is a very similar plot, but just again showing the timescales and the relative luminosities of the different emission components that can come out. The gamma rays in particular and hard X-rays is what we'll be focusing on here. Here it shows that they peak at 10 to the 46 ergs per second. This is for 170817, which we now know is off-axis. For on-axis short gamma ray bursts, this is more normally like 10 to the 51 ergs per second. And then depending on your inclination angle of the binary neutron star merger with respect to our line of sight, what happens can vary. But if it's on axis, you have this monotonically decaying afterglow, broadband afterglow. If it's not on axis, then the afterglow will actually rise before decaying and on much longer timescales. And then, of course, you have the thermal component. which is the driven by the radioactive decay of the R process elements that get synthesized in the kilonova. But you see that there's very interesting stuff happening in the first tens, hundreds, or even thousands of seconds of the merger, and 170817 wasn't found until 5 or 6 times 10 to the 4 seconds, so around here. Really what we want, right, is to get on target with Hubble, Chandra, VLA, and our best sensitive facilities at very early times. And in order to do that, we need to provide a localization. This is just showing this huge missing time frame here where there was no sensitive UV, X-ray, optical, IR, or radio observations of the early time post-merger environment for 170817. We all know that a huge amount of work went into this plot, thousands of astronomers, but despite that, we couldn't get on in early times. We really need to be specific about one reason we might want to be observing at early times. For 170817, there still exists uncertainty on exactly what the emission processes and the progenitor model that drove the kilonova emission were. Here's examples of 4 models that were compiled in Yair Kavli's paper from 2018. And what the data, right, the photometric data points that for the kilonova are the dots, and the models are the solid lines and the dashed lines on both panels. And what you see is that at late times, the data agree very well with the models, all of the models. It's only at early times, and actually only at early times in the UV, that you can really break these model degeneracies. So you need very early time observations, particularly on the blue side, to break the model degeneracy and to really understand how to model the kilonova emission. There are other open questions that remain from 170817, many of which could be addressed by earlier time observations with sensitive facilities. These are just some of them. I'd be happy to talk about any of them, but there's a lot of questions. So then you might say, right, well, the reason that we didn't get on target early times, right, is because gravitational waves are poorly localized on the sky. This is exactly the problem. If the gravitational waves came out with the arc-second localization, it would be trivial to get on target with our most sensitive facilities, just stare at it with Keck immediately or whatever. But that's not what happens. Gravitational waves are very poorly localized on the sky. So far, the median localization is many thousands of square degrees. What you're looking at here is a panel from the gravitational wave treasure map, which I built with Sam Wyatt at the University of Arizona and some other people. And it attempts to provide a platform to collate and collaborate the worldwide electromagnetic follow-up of gravitational waves to search for their counterparts to hopefully optimize it so we can find it. In particular, the panel that you're looking at is for the gravitational wave 190814. 190814 is special for a few reasons. It's a very high mass ratio event that with its initial reporting, the smaller component mass might have been consistent with the neutron star mass. It's probably actually a very low mass black hole. But even more important, and the reason it's on the screen is because this is the best localized gravitational wave source to date. It was localized on the sky to less than 20 square degrees. You can kind of see the red lines as the outlines of the 90% containment region for 190814. And all of these boxes, color-coded boxes on top of it, are reported pointings of electromagnetic facilities that attempted to search this 20 square degree error region for an electromagnetic counterpart, and most of them were targeting the kilonova. In particular, there's actually 4,000 search exposures from different instruments spanning the electromagnetic spectrum, and it looks like, since you can barely see the gravitational wave containment contours, that the coverage is very good, and we probably searched it very quickly because it's small in the sky. And that's actually not true. If you time resolve the coverage of the gravitational wave localization region on the sky, what you see is that while eventually we did indeed cover most of the gravitational wave localization region posterior, that's what you're looking at here, the percent of the gravitational wave localization region that was covered as a function of time, it actually took us 2 days, even for this best localized gravitational wave source to date at 20 square degrees on the sky. And most of them are much, much, much larger error regions than that. If there was, in this case, there probably wasn't an electromagnetic counterpart to be found, but if there had been, and if there had been something at early times, we would have missed it, even in this best case. And that's just because we have to search large areas of the sky. And even if you search the whole thing very quickly, you're going to find tons of supernova, tons of contaminating transients, and it's going to take another couple of hours at least before you can spectrally classify your candidates, pull the kilonova out from all the other candidates, and have the community coalesce around it before we can trigger our most sensitive follow-up facilities like Hubble, Chandra, VLA, whatever, to actually stare deeply into the immediate post-merger environment. So one, it takes a long time to search these localization regions, even when they're small, relatively. And two, even if we could do it, you have to add another lot more time to actually, trigger the other facilities, right? This is multi-stage process of searching these gravitational wave localization regions. What if we didn't have to do that? In addition, I'll point out that in the 3G era, so this is with the next generation gravitational wave detectors like Cosmic Explorer and Einstein telescope, the binary neutron star mergers that will be detected at distances that even if you could search with our best facilities like Vera Rubin, the localization regions, the kilonova is just intrinsically too faint to recover, right? The kilonova is, it's less luminous than a supernova, certainly less luminous than a gamma ray burst, and Cosmic Explorer will be detecting binary neutron star mergers at Z of 1.5, and you just can't find the kilonova out this far. So we need another emission component, and ideally one that we can, use to localize these things at very early times. And I'll posit that the GRB is a good thing to do this to solve our problem. It's sometimes bright, sometimes it's not bright, but importantly, it's prompt. Right? The kilonova actually takes a few hours to rise. So if you want to stare into the immediate post-merger environment and you're trying to find the kilonova to do it, it's not really going to happen, right? Because the kilonova rises on the time scale of several hours. The GRB, on the other hand, comes out promptly within a few seconds of the merger time. And we have wide field of view facilities, STROBE-X will hopefully be one of them, that can monitor the whole sky or close or large fractions of the sky and don't have to do the arduous and slow and time-consuming task of searching these gravitational wave localization regions, which is critical. The one time this has been done, right, was for 170817, and you're looking at that on the left. Both Integral and Fermi detected a short gamma ray burst counterpart to 170817, coming about 1.7 seconds after the binary neutron star merger time. But unfortunately, they couldn't solve our problem because the Fermi and Integral localizations on the sky were actually worse, right, than the gravitational wave localization. The gravitational wave localization is in green. The Fermi localization is in purple. It's about 1500 square degrees. And the timing annulus from the IPN, from the interplanetary network, between the Integral and Fermi time offsets is this gray timing ring. So although they didn't have to search the sky to detect this, right, because they were monitoring close to the whole sky, they couldn't provide the localization. But there is a technology whereby we can provide prompt arc-minute scale localizations to gamma ray bursts. And arc minutes is important, right, because one arc minute or a couple of arc minutes fits within the Hubble field of view. Fits within the JWST field of view, right? This is the type of scale that you would need to bypass the requirement to do wide field searches of the sky and just immediately slew on target with our most sensitive facilities. The most sensitive and largest coded aperture imager to date launched is the Swift Burst Alert Telescope. Hopefully in the future, this will be the STROBE-X wide field monitor. The way that you localize gamma rays and hard X-rays with a coded aperture imager is you put a opaque pattern mask above your detector that spatially encodes the incoming direction of the gamma rays and X-rays via the pattern, the shadow that's cast on the detector through the opaque mask above, right? So you have some gamma ray sources. Sorry, this is probably in the way. You have some gamma ray sources. They're shining through this mask. It's made, in this case of Swift-BAT, of 55,000 lead elements resting on a composite layer. If the gamma rays hit the lead is opaque up to about 200 kV, and they don't go through. If they hit the composite, they do go through, and you cast a shadow. In reality, there are many partially overlapping shadow patterns, but if you're smart about how you set up your mask pattern, then you can break all of these shadow degeneracies and reconstruct computationally the distribution of sources on the sky that created this shadow pattern. And the way this is typically done is you take your shadow pattern that's cast onto the detector plane, and you do a cross correlation with the known mask pattern to reconstruct the sky image that created it. To give you some sense of scale for BAT, the detector plane is 0.5 square meter, the mask is 2.5 square meters, and the distance between the detector plane and the mask is 1 meter. So it's a big thing. It's the size of your dining room table. Okay. Intrinsically, BAT is also the most sensitive GRB detector. And this is very important, right? because what we saw for 170817 is unlike most GRBs, as I mentioned before, that are about, short GRBs, they're 10 to the 51 hertz per second or so. It was very, very faint, underluminous by a factor of 10,000 compared to the cosmological population. We know now that this is almost certainly because we were looking at this binary neutron star merger at 20 to 30 degrees off the orbital angular momentum axis, and assuming that the jet aligns with that axis, therefore we were looking at a similar off axis to the jet, and this is why the gamma ray luminosity was significantly suppressed. But because it's so weak, we have to have very sensitive detectors to detect these things in the local universe, right? In the distant universe, we can see these jets, out to more or less arbitrary redshifts, but for things that are off axis in the local universe, they're quite faint. And in particular, for fermion integral, 170817 is undetectable beyond 60 to 70 megaparsecs. Luckily, BAT is more intrinsically sensitive, and if you could get the time-tagged event data, you can do very sensitive searches, one, to detect it, and two, to provide these, critically, these arc-minute scale localizations. The problem with Swift was that it was not designed for this. Swift's mission design, right, was to promptly onboard localize gamma ray bursts to arc minutes within about a couple seconds. And there was no requirement for non-real-time analysis. And because the effective area of the BAT is so large, and the solid state recorders are limited, and the bandwidth of our downlink is limited, we can't actually bring all of the time tagged event data to the ground. And we'll get into the setting for STROBE-X in a little bit. But what that meant is that we couldn't do sensitive targeted searches on the ground, which is unfortunate. And it means that for the first 15 years of the 16 years of the Swift mission, we relied solely on these onboard triggers to find GRBs. Luckily, and I'm getting into these technical details because they'll be important for later, the data is saved onboard the spacecraft in a ring buffer. And that ring buffer lasts about 20 minutes before it starts to overwrite itself as a ring buffer. So if you could get a command to the spacecraft within 20 minutes of a gravitational wave, you could save the time-tagged event data. Remember, and the event data is a list of counts, presumably photons, but they're not always photons, that are tagged with the time of arrival to 100 microsecond relative accuracy, the energy, somewhere between 15 to 500 keV, and the detector, the XY position on the detector plane. If you could get a command to the spacecraft within 20 minutes of a gravitational wave, you could save this data out of the ring buffer before it gets overwritten, bring it to the ground, do these sensitive analyses, find and localize the burst, and profit, or just fall in love with the mysteries of physics. The problem, until a couple years ago, was that the fast response commanding that exists for space telescopes, and Swift was the fastest, was 2 to 4 hours, which is woefully inadequate if you need to get a command up within 20 minutes at any time of day. So we addressed this. We built something called GUANO, which dumps the BAT and dumps the ring buffer of the BAT on demand, fully autonomously. So triggers come in from external instruments. They go to the Swift Mission Operations Center. They trigger GUANO. GUANO autonomously schedules and gets in contact with the spacecraft and tells the Burst Alert Telescope to dump the event data in a 200-second window around the time of interest, the gravitational wave, of the fast radio burst, of the neutrino, whatever it is that you want, and brings it down to the ground. What you're looking at on the left is the latency that we're achieving. We've now done this about 3,000 times, fully autonomous commanding. And to our knowledge, this is also the first fully autonomous commanding and on-demand commanding of a space telescope based off of scientific triggers and scientific purposes. And crucially, it will also enable a few other applications to have autonomous commanding of the space telescope is very important. Right now, the median time that the GUANO command is sent is T0 plus 15 or 16 minutes, but this is from the astrophysical T0, right? So this includes any latency from the triggering instrument side, right? So that if the gravitational wave detector takes 2 or 3 minutes to send their alert out, that's in here. But almost all of the time, this is fast enough to get the data out of the ring buffer and save it before it gets overwritten. The things that are negative below the red line here are things that we didn't get to in time. And this can be because we were too close to the South Atlantic anomaly, so the ring buffer filled very quickly as the background increased, or other things. Okay, now that we have the event data on the ground, we can do the typical cross-correlation imaging I was talking to you about before, right? Where you take the shadowgram on the detector, you cross-correlate it with the mask pattern, really what this looks like is a complex multiplication and a fast Fourier transform. And this is a very simple analysis technique to do. And it's been done with coded aperture imagers for 40 years or more, 50 years, and localize your source. But the problem, we realized a few problems. One is this technique results in a large image noise population. When you construct these sky images, if you search naively, or if you just search for sources in these sky images, and here on the top panel is a list of the sources in sky images that are found in sky images as a function of their SNR, and this is the reverse cumulative distribution function, right? So this is the number of sources in sky images found with SNR greater than X. You see that for BAT, at least, at SNR 6.8 or so, the distribution goes from signal dominated, all of the things over here are real GRBs, to noise dominated, these are all fake. If you do a log linear extrapolation of the real sources into the noise, you see that there are real sources there that we should be able to find, but they're totally dwarfed by the noise, these fake sources in the images. And this is something that is intrinsic to coded aperture imaging. In addition, though, and even more importantly, this image cross-correlation technique rejects information that's stored in the event data, right? You are intrinsically binning over energy information, over temporal information, and over some other information as well that you could use in principle in a search. In addition, any coded aperture imaging technique that does cross-correlation pays a mask weighting efficiency factor. This can be interpreted in many ways. It's often called the coding power. It really has to do with the resolution elements on the detector having a fuzzy or imperfectly resolved image of the shadow that's cast. And the effect of this is the following. If you just calculate the effective area of BAT, of the detector, in count space, you get this blue curve, which peaks at about 2,500 square centimeters near 100 keV. However, if you apply the cross-correlation imaging technique and you calculate the effective area again, it's this orange curve. It's cut in half. It's actually not exactly half, it's 54%. This is the coding power of the instrument. This is the mask weighting efficiency I was talking about. This just comes from doing the mask weighting and the cross-correlation technique. In addition, the cross-correlation imaging is necessarily going to have lower effective area at high energies because the mask, even though it is supposed to be opaque, starts to become transparent to X-rays and gamma rays above 150 keV. So you get a factor of 2 difference in the effective area at low energies, but the effective area difference at high energies can be a factor of infinite. So this is interesting. So what we wanted to do was figure out, okay, is there a way to exploit the full effective area and sensitivity of the detector while still achieving the arc-minute scale localization that we've typically needed the imaging technique to do? And the answer actually is yes. So the technique that was developed mostly by Jimmy Delany, who at the time was a graduate student at Penn State and is now at the University of Alabama working on IceCube, is called nitrates, the non-imaging transient reconstruction and temporal search. And instead of taking the data and cross-correlating it with the mask, instead we do a full forward model of the coded aperture instrument. And this will be applicable to STROBE-X as well. And if you do this, you can exploit the full effective area of the detector while simultaneously having the discriminating power to do arc-minute scale localization, right? What you're looking at on the bottom is not real data. This is simulated data. So this is a GRB with this fluence coming at the detector from these angles and casting a shadow onto the detector. What you see here is the coded region, right? So this is the portion of the detector that, given the angle that the GRB is coming in on, is casting a shadow onto the detector plane. The arc-minute scale localization is encoded in this rapidly changing response. But what you see is that there's also non-zero counts in parts of the detector plane that don't have a shadow cast on it by the mask, where counts come in through the sides of the instrument, right? And what you're looking at here, it'll become more clear if we look again here, right? In this case, a GRB is coming out from the side, and it's somewhere not in the fully coded field of view. Only part of the detector plane has a shadow of the mask cast on it, but it's coming through here, and these structures around the sides of the instrument also cast shadow onto the detector plane, but they're not perfectly opaque, right? So counts get through there. Coded aperture imaging necessarily assigns a 0 weight to these counts and throws them out. So they cannot contribute to the signal, but if you have a full forward model, you can. And so this is one way among many in which the sensitivity is increased. In addition, you can detect GRBs that come totally outside of the field of view of the instrument, right? This is a GRB that's coming totally from the side. It's not along any angle by which a shadow is cast on the detector through the mask, but there is structure encoded on the detector based off of the passive materials that surround it. And in principle, you can use this for coarse localization, not arc minute scale, but coarse. I'm going to skip over some of this technical detail because I want to have time to discuss things. But basically, this is how we set up our maximum likelihood method for comparing the simulated data to the observed data with a likelihood test and formalizing that into a search. This is more stuff. We actually model the background and all of the galactic sources that are simultaneously casting shadows onto the detector, not just the GRB. The responses are very complicated. In order to do this, you have to have a very good understanding of your response function of your instrument along every line of sight. Nitrates is systematically limited. The sensitivity now is systematically limited by our uncertainty in the response functions. That could be solved with better on-ground calibration. Unfortunately, Swift has been in space for 18 years, so we can't do that, but STROBE-X could do it. And we're trying to do it now on-orbit data-driven calibration, but it's hard. This is what constructing a response function looks like as a function of instrument angle. I'm just going to go through this stuff. We've turned it into a search, right? So now that we have the data on the ground fully dumped by GUANO, we have the raw event data. We want to do a GRB search with nitrates with this forward modeling maximum likelihood search. So we formalize it into a search. The parameter space is very big because the BAT field of view is 7,000 square degrees and the PSF is about 15 to 18 arc minutes. There are many positions to check, right? When you want to do this in a search, it's much more sensitive than decoded aperture imaging, but you pay a factor of 1 million or more in CPU time. It's much more computationally costly because you're actually simulating GRBs coming from all over the sky through the instrument, comparing the simulated data to the observed data with the likelihood test, doing that for every position on the sky and many grid points in spectral space to find the GRB position. So it's much more computationally costly. We do a lot of seeding rounds. I can talk about that if people are interested in it, to cut down the temporal and spatial parameter space. Within the coded field of view, this is in BAT image units. Here, 1 unit is about 40 degrees on the sky. We do a coarse graining. We simulate GRBs at that position, make the simulated data on the detector plane, assuming a GRB with different spectral parameters, priors at that position, find the best fit. Then we zoom in, do another grid, find the best fit, zoom in even further, do another grid of simulations, and eventually we find the maximum likelihood position, which is the true GRB position. It's much more sensitive than coded aperture imaging. On the left, you're looking at the results of coded aperture imaging, the image sources that we find as a function of SNR. This is for a test GRB, a short GRB, 180805b. You see that this is in blue as the SNR found in different images at the true GRB position. It looks pretty good. And then the noise population that I was talking about before. It's large and and starts blowing up above SNR at 6.8. In this case, it's a little suppressed. This is the comparable results from nitrates. So first of all, you see that the true GRB position has an enhanced significance compared to coded aperture imaging. And the square root of our test statistic is purposely constructed to be comparable to the SNR. But crucially, you see that we have dramatically suppressed the noise population. We only paid a factor of 1 million in CPU time to do this. But if you're very motivated to find faint short gamma ray burst counterparts to gravitational waves, this might be worthwhile to do. I would posit that it is worthwhile to do. And in addition, this type of search is embarrassingly parallelizable. So all of those simulations for the forward models that we have to do in the search are independent. And so if you throw CPU at it, you can bring, even though the CPU time is high, you can bring the wall time down to near zero, or at least short. And actually, this is what we've been doing. So GUANO came online in December 2019. Started listening to gravitational wave triggers in the second half of the third gravitational wave observing run. A couple months later, we were like, well, what if SWIFT-BAT is actually missing GRBs that are detected by other instruments on board for some reason? So we started listening and triggering GUANO on GRBs detected by other instruments, Fermi, Integral, CALET, HAWK, also CHIME, IceCube, other instruments. These are, for the GRB instruments, these have either large localization regions from Fermi, hundreds or thousands of square degrees, or from the other instruments, no localization. The result has been that we're actually finding that SWIFT is missing many GRBs that are intrinsically detectable and localizable with our new analysis technique on board. Mostly this is because they're at the edge of the coded field of view where the sensitivity falls off, but not always. The onboard searches are always going to be less efficient than what you can do on the ground. The rate of things that we've been finding is one extra arc-minute localization GRB per month. This is actually now outdated. This number should be 31 GRBs. To give you some context, this is a greater than 15% increase in the worldwide rate of arc-minute localized GRBs just from software. People pay, and design missions tens of millions of dollars to get a GRB rate like this. Because the nitrates technique also increases the effective area, particularly at higher energies, which is important for short hard bursts, the short GRB recovery fraction as a fraction of the total GRB rate is much higher, 25% for guano and nitrates versus only 10% of BAT onboard detected GRBs are short. And crucially, we could always use more compute, but we have a couple hundred CPUs. This is running all the time, and we are getting these detections and arc-minute localizations out to the community fast enough that they've been able to follow them up with focusing instruments in the soft X-rays and the optical to find the afterglow. And it's been done fast enough, and it's been done successfully. These numbers are also updated. Now the number is 13 X-ray afterglows have been discovered from faint GRBs that we find. A couple of these actually also have redshifts that were found from optical facilities, but most of them are just in the X-ray. So the idea is we want to do this for a gravitational wave source, right? This is just for GRBs coming from other facilities, but eventually we want a gravitational wave trigger to go through this same loop, and we want to make this faster. I'm going to skip that. This is the searches that we've run to date. These are as a function of source type, fast radio bursts, gamma ray bursts from other facilities, gravitational waves and neutrinos, the successful dumps of guano event data and nitrate searches that were run. The takeaway here is that we've done this many thousands of times, fully autonomous space telescope commanding and targeted searches, and we're doing those targeted searches and data downlink fast enough to get arc-minute scale positions to the community for follow-up. I'm going to skip this. This is just, we're doing a joint subthreshold search with the LIGO, Virgo and Cogro collaborations and their MOU, where we take the subthreshold things that we find in Swift BAT guano nitrates and compare them to the subthreshold gravitational waves. The reason this is important is because the joint GRB gravitational wave horizon is much further, and the total space-time volume sampled much greater than just the gravitational wave horizon. And this is critical for increasing the rate. So this is something that's coming out. I don't want to get into the technical details right now. The result is that we have increased the maximum recovery distance for a 170817 light burst, remember, and this is something that's about 10,000 times weaker than the cosmological population, out to about 115 megaparsecs. This is actually, we've done a little bit better now. I think the number is probably 120 megaparsecs now. And for reference, again, compared to GBM onboard detections and Fermi GBM targeted search ground analysis, this is much farther. However, the kicker, right, is that the BAT field of view only covers 7,000 square degrees, only 1/6 of the sky. In some cases, like this GRB trigger, this gravitational wave trigger, sorry, 200114F, you get lucky and the gravitational wave just happens to land in the BAT coded field of view. This will happen 1/6 of the time, right? Because BAT covers 1/6 of the sky. But what can we do about that, right? We don't know a priori where gravitational waves will come from before they happen. But actually we kind of do. And this is because the gravitational wave detectors have non-isotropic sensitivity across the sky. They have antenna lobes and antenna patterns, and you can exploit their known antenna patterns and systematically schedule Swift or STROBE-X to point in the direction of the gravitational wave antenna lobes as they circle across the sky. And in this way, you can increase the joint GRB gravitational wave co-detection rate and correct for the fact, at least to some extent, that your instrument doesn't cover the whole sky. And the result from doing this simulations to do this with Swift is below. This is real Swift schedules from the year 2017 as a function of the day of the year. And on the y-axis, this is effectively how many of the gravitational wave sources fall within the BAT field of view. So this is blue is the actual Swift performed schedule, and you see it hovers around 16%, which you would expect from BAT covering 1/6 of the sky. If we had full control of the Swift instrument and it wasn't doing any pointed science with XRT and UVOT, you could actually close to double this. and bring the fraction of gravitational wave sources that land in the bat field of view up to close to a third. Of course, Swift and STROBE-X will have pointed instruments that want to do pointed science, so they can't always point directly at the gravitational wave antenna lobes, but you can balance this and just look at those targets that you want to look at when the gravitational wave antenna lobes happen to be over them if you don't have strong temporal scheduling constraints, and you could do somewhere in the middle. So you can basically increase the effective field of view and your effective rates from 1/6 of all events for BAT to 1/4 of all events, and STROBE-X can do even better. So this is one thing we can do to correct for the fact that the coded aperture images just don't cover the whole sky. But even maybe more excitingly, but also more crazily, maybe we could do something better, right? So what you're looking at on the left is something that happened in gravitational wave observing run 3. The portion of the sky that's covered by the BAT field of view is in green. This is 7,000 square degrees. The portion of the sky that's covered by the Earth occulted, because Swift is in low Earth orbit. At any time, the Earth blocks 30% of the sky. This will be the case for STROBE-X as well if it's in Leo. And here is the gravitational wave localization region. It is outside the BAT field of view. So if there was a GRB there, maybe we would have been able to detect it through the sides with nitrates, but we certainly wouldn't have been able to provide an arc minute scale localization. The question is there anything we can do about this? And the answer is maybe, right? So the many people in the gravitation in LIGO and Virgo and Kagra are working on what they call early warning gravitational wave detections. That is that binary neutron star mergers can enter the sensitive frequency band, the bucket of the gravitational wave detectors a long time before merger. 170817 was in the detector for almost 100 seconds. You integrate SNR with each cycle, and there are many thousand cycles between the time that it enters the gravitational wave detector sensitivity band and when it actually merges. And in principle, you can claim a detection before merger time by running your match filter with truncated templates. Of course, your SNR will be lower, and so your sky localization will be larger, but we have 7,000 square degrees. What if they could tell us, 100 seconds, 50 seconds before merger, hey, go in that direction, and we could torque the spacecraft around and put the gravitational wave region in the coded aperture instrument field of view. This is not just a hypothetical. People like Ryan McGee, Surabhi Sachdev, and other people in LIGO are working very hard on getting this, and they're going to deploy it in 04. They actually did a data replay run right after 03, where they successfully sent alerts before the merger time from played back data. So what would this look like for a space-based instrument to try to respond to it? This is a simulation on the left for a possible sky configuration at the time. So the idea is that Swift is pointed at this red point on the sky at start time. Every pixel on the sky is color-coded by the amount of time it would take to get that sky pixel into the coded field of view of the coded aperture instrument of BAT. Over here is the part of the sky that's blocked by the Earth, right? The Earth isn't moving out of the way for you. I mean, it will if you wait for half your orbit, but not if you just wait a couple hundred seconds. In purple and black are things that are already in the back-coded field of view. But what you see is that within 100 seconds, large fractions of the sky would in principle be accessible to Swift. And this is with a slew rate for Swift of 0.8 degrees per second. This includes the recent reaction wheel failure of Swift, so only 5 reaction wheels, and the torque available in the attitude control system capabilities of our current setup with Swift. I'm told, Tom told me recently, that STROBE-X can expect 3 degrees per second, which is just an excellent thing to hear, because it'll make it even better. And what you're looking at on the right is doing many thousands of these simulations based off of the position of the Earth, the sun, the moon, all the observing constraints, where Swift is pointed at a given time, feeding in realistic gravitational wave early warning alerts and sky maps, and seeing, okay, how much time do I, as a function of the negative latency of the early warning time, what fraction of the sky can I actually get into the coded instrument field of view before the things merge, right? To actually, make sure that we're on target at the time of merger, catch the prompt emission, localize it to arc minutes, and solve all of physics. The answer for Swift BAT is it's going to be very hard. One, we only slew at 1 degree per second. That's actually pretty fast, but only 1 degree per second. Two, BAT only covers 7,000 square degrees. The wide field monitor on STROBE-X will have a larger field of view. And three, the current generation of gravitational wave detectors, how early they can produce these alerts is fundamentally limited by their low frequency sensitivity. But the answer is that with 50 seconds of early warning, we could plausibly double the sky rate. We could get twice the amount of sky that BAT covers just automatically in the BAT field of view. And this is worth doing. It requires, right, effectively instantaneous spacecraft commanding. And you might have remembered, if we go, oh, I shouldn't have done that. If we go all the way back, right now, even though GUANO is fully autonomous and it's doing the lowest latency spacecraft commanding to date, it's still only achieving, order 15 minutes. That includes an extra 2 to 3 minutes on the alert side, but really GUANO is only achieving 13 minutes of for the minimum median achieved commanding latency. This has to do with specifics that I cannot get into about how the NASA TDRS network works. Remember, TDRS is the constellation, the geosynchronous constellation that we use to talk to our low Earth orbit spacecrafts when they're not directly in line of sight with ground stations, which is most of the time. So if you want to get a command to Swift now, you send it to the White Sands missile range where TDRS is operated. They send it up to the geosynchronous satellite that's always sitting above White Sands, New Mexico. It bounces around the constellation until it finds a geosynchronous satellite in the TDRS constellation that does have line of sight with Swift, and then beams it down to Swift. There's a fundamental lockout right now that prevents GUANO from going faster. Almost all of this latency does not come from GUANO, it comes from TDRS. But working with the NASA engineers, they actually think that this is possible based off of continuously scheduling and keeping a continuous contact open with Swift. The fundamental lockout right now, actually, for the latency, this 10-minute lockout comes from the need to schedule a new contact to begin on demand. But if you just always have a contact open, the actual intrinsic latency of the command from our Mission Operations Center to Swift in low Earth orbit is less than a second. And we think that we can pull this off. And we're going to try, is what I'll say. I say we're going to try really hard to pull this off. But as I said, the prospects in 04 are not great for early warning response. Given a realistic population of binary neutron star mergers and a 1-year observing time, in blue is what you expect the detection rate per year as a function of the early warning time. So what time the alert comes out before the merger time, the negative latency, and that you see at 10 seconds before merger. In this blue population, you can expect maybe 1 or 2 events per year. But you saw that for Swift to do anything really interesting with this, we need like 50 seconds pre-merger, and then it's just not going to happen. The blue population here is assuming 0 latency for the LIGO pipeline. Of course, the LIGO pipeline doesn't have 0 latency, and if you assume a realistic latency, you're looking at this red curve. This is for a realistic binary neutron star merger population. If 170817 happened again at 40 megaparsecs, we would definitely be able to detect this and LIGO would be able to produce an alert at T0 minus 60 or 70 seconds. So it's worth being ready for it and preparing for it. But realistically, the rate of binary neutron star mergers at 40 megaparsecs is like 1 every 10 years. So it's unlikely, but we should still be ready. Here you're looking at the cumulative, the number of events per year as a function of the localization area, right? So if you and the latency pre-merger, right? So if you choose an earlier time before the merger, you have less SNR in your signal, so your localization area of your gravitational wave is larger on the sky. If your field of view is many thousands of square degrees, you might not care, but that's just something to keep in mind. So 04, the prospects are not good for pulling this off with Swift, but I think it's incumbent upon us to try, because the yield of a prompt arc minute scale localization of a gravitational wave detected by a neutron star merger and access to the post-merger remnant environment is just so exciting that I think we need to try. But critically, we need to try so that we can demonstrate that these novel operations modes, fully autonomous space telescope commanding, fully instantaneous, continuous commanding, stuff like this, are risk retired on orbit and have heritage, so that they can be put in the STROBE-X mission design. And STROBE-X launches with that capability instead of what we had to do, which is engineer it with a system that wasn't meant to do it 15 years post-launch. Things start to look better in terms of the rates for early warning response in 05. But for the next generation of detectors, 2.5G, not Cosmic Explorer Einstein telescope, but things that would fly in that would exist in the early 2030s when hopefully STROBE-X would fly, the rates look really, really good. We're talking about many events, tens of events per year that have early warning alerts greater than 100 seconds pre-merger. And this is a reasonable thing to do because, right, STROBE-X will have a larger field of view than Swift-BAT. With all the camera pairs, it's going to see maybe a third of the sky, not 1/6 of the sky, and 2, slew faster than Swift-BAT. And so I really think that there's a amazing opportunity, even without early warning response, with STROBE-X, even for things that happen to land in the 1/3 of the sky that STROBE-X is, instantaneously observing, to provide arc-minute scale localizations of the gamma ray or hard X-ray counterpart to binary neutron star mergers. But we can actually increase that rate by systematically biasing the scheduling of STROBE-X to point in the right direction at the right time based off of the gravitational wave antenna pattern. And we can do even better and be even more aggressive by torquing the spacecraft quickly across the sky in low latency in response to these triggers. I'm going to stop talking now because I hope that, right, so I talked about, I'm going to say one more thing before I stop talking. I talked a lot about Swift-BAT because it is the coded aperture instrument that is most productive and operating today. The wide field monitor on STROBE-X will be more performant along several axes, but it'll be less performant along some. In particular, and something that's a concern for me for gravitational wave counterparts is the energy range. It goes from 2 to 50 keV. Short gamma ray bursts are harder than this, right? They do have emission below 50 keV for sure. We see some of them have extended emission that's soft. 17817 might have had a soft thermal component, but the main peak, for 17817 had an E peak of 200 keV, and some of them are even harder than this. So you're intrinsically limiting the sensitivity by having a limited energy range. All of that being said, though, the localization capabilities of STROBE-X are even better than Swift-BAT. The field of view is even larger, and I think we have an excellent chance. In fact, I think we can guarantee, given the rates, that STROBE-X will be able to provide an arc-minute scale localization to a binary neutron star merger at very early times to allow access to the post-merger environment. Thank you.
All right, so let's thank Aaron.